a really, really generous introduction. Thank you so much. It's a great pleasure to be here. One of the things that I decided that I would talk to you about as I looked through this slide was some pretty raw work, so I apologize for that in advance. These are all kinds of problems we started working on in the last sort of 18 months or so. And as a result, they're necessarily kind of raw. I'm going to tell you a little bit of history about why we started working on these problems and why almost everything now that's coming out of our lab is based on a small kernel of an idea, which is kind of summarized with this beyond hand label data. Now, in this talk, there are really sort of two pieces, sort of two premises that are going on underneath the covers. One of them is that if sort of machine learning and AI tools are really going to have the impact that we hope that they have, then they're going to have to move beyond sort of just confined to a small number of companies and PhDs and the rest. They're going to have to get out there and start getting dirty with the domain scientists. And I'll tell you a little story when we start to explain to you our little weird journey and why we started working with some of the domain scientists. The other premise is that deep learning is all the rage, but it really means that a bunch of tasks are basically becoming a commodity. There's not that much margin in building a better model or adding more automatic featurization. And also, there are billions of dollars, that's not an understatement, flowing into making those models work better and then be published online. And so sort of almost as a pragmatic thing, about 2 years ago, we said, well, if people are going to make better models and they're going to spend a bunch of money, that's great, you're making our lives easier. But we're going to have to worry about kind of what comes next. And one of the things that became clear right away was that to get some of these interesting models to work, you still had to figure out how to get some amount of expert knowledge from someone's head into code and into the training data that you were using, even if you had a fantastic model. And so we started looking at exactly how does that happen, that wild and woolly problem of going from specification down into code. And it turns out that you can actually put some structure on it. And we considered a couple of different alternatives, most of them bad ideas. We tried to constrain the models with prior knowledge, which was like a very natural thing given some of the work we had done before. We couldn't get that to work. We then settled on something that was kind of unsatisfying, but was this idea of generating training data, and generating training data according to particular specifications. And basically, that's the way you program. And I'm going to tell you about that project called Snorkel. I'll put up links throughout. You can go check it out and see exactly how it works. And it's a new project, so please flame us, tell us all kinds of things. And it builds on an incredible amount of related work. We tried to put up a blog that lists a bunch of the related work, but even that is woefully incomplete. So please send us your feedback. Now, to see where we're going, since it's kind of still early days in the project, you kind of have to understand what we were doing and why we got into this mess. So let me give you just a 5 or 10 minute overview of what we had been doing and that story about why we want to work with domain scientists. So for about 5 or 6 years, we worked on these problems that we call dark data problems. Dark data is easy to understand by contrast. Things that are not dark are things like clean, structured SQL databases, spreadsheets. These are data that are really precisely and well understood by machines. Once your data is in that format, it's really easy to build an application. Now, the problem we were looking at previously was that a lot of data is not first born in that clean, structured form. It's born in things like scientific articles, research articles, government reports, medical images. These are all things that natively machines don't understand the semantics, and we have to work pretty hard to translate those low-level bits, basically, into those high-level, sort of cleanly understood pieces. Now, when we started this, there are very many subfields of machine learning and AI that are represented here, computer vision and NLP. And our goal wasn't to be a better machine learning or NLP system. Our goal was to really try and figure out how we could go from where the data start, that's in that format down there, all the way to the end, using the best of all breed tools. And so we built this system called DeepDive. Its first version was exactly that. It was basically just a graphical model inference layer based on Markov logic that was allowing you to stitch together the world's best models that were out there so you could grab them, put them together, and build something end-to-end, and then do inference across them. We were really excited about that. We even won some NLP competitions just to show that you could do some interesting NLP things. And we built and released that system. One of the things we didn't expect that happened about 2014 was that we showed for some actual applications, these are from a Nature article, that actually you could start with the same PDFs that geologists in this case were reading and go all the way to the structured database that they were producing with higher quality than human volunteers. That is, the folks who are helping build this database anyway. And this was no small effort. They had spent 2 continuous person decades actually constructing that database. So it was really exciting that the system, the automatic system, could actually compete and in some ways be better than that system. But of course, as sort of machine learning and AI researchers, you don't really care about being better on geology paper. You want to do better on a range of different things. And so with these two students who are great, and I can't help but plug them, my first two PhD students, Sejong, who's now a professor at ETH, got written up in Science recently. Let me brag about that. He just did this thing called Galaxy GAN. You should go check it out. My student Feng Wei made a very bad decision. He decided after graduation that he would go to Google for a little while. That wasn't a bad decision. The bad decision was that he then decided to start a company with me, a company Lattice, and he has been hanging out in coffee shops for an embarrassing amount of time writing code with me, and now we're at Apple together writing code. But all three of us had this vision that we were going to take this thing and apply it everywhere. Okay? And so we did. But honestly, it was those two guys applying it everywhere. We applied it to this biodiversity problem that I mentioned. It still runs there today. Once it was set up, they were running. We did a bunch of stuff in drug repurposing, lung cancer prognosis, I'll talk about next. One of the things I'm most proud about in my career is that we got to help with this anti-human trafficking effort. So we read 100 million ads for sexual service inside the United States and screened them and told law enforcement where they should actually look for human trafficking rings. And that's running every day. We're really excited about it. The guy who ran it is a guy named Chris White. That's him right there. That guy's John Kerry. And John Kerry's putting a medal around his neck, which was a medal from Barack Obama for this project Max. And we were really excited about it, that we were having societal impact by bringing this technology out there. And so this infected us. When I talk about how we want to take our technology and throw it over the wall, in most of these cases, throw it over the wall meant that a PhD student or two were effectively sacrificed on our side to building a system so that one of these great things can happen. And luckily, we have great PhD students who sometimes should ask more questions, but then end up building these great systems. And then we also built this company, Lattice, that was mentioned earlier, and that's now part of Apple. Okay. So this was really exciting. But as I mentioned, these were kind of one-off events. Right? Now, what I want you to take away from that is just like we're building things, we care about actually building things that people and end users can use. But let me tell you a little bit more about one of those applications in detail, which is this healthcare application. And hopefully you'll find this stupid little story interesting, and it was at least eye-opening to me. Okay. So all my examples are very grim. I should warn you about that before I say that. We're going to talk a little bit about lung cancer. Lung cancer is bad. That's what the slide says. Early stage lung cancer, die about 50% of the time. Late stage lung cancer, you have about a 4% survivability. Okay. All right. So we looked at this lung cancer problem of diagnosis. You show me sort of a patient record and try and say, is this the kind you're going to die from quickly or slowly? And this paper took a little over 2 years to construct. The star bar shows this guy Kuhn, and so did a lot of work too, but Kuhn did really amazing work. He's the one who's going to be starring here. Okay. These are all the folks, that's Kuhn. Okay. Now, what happened was Kuhn came to my office, literally just showed up in my office. It was amazing. This is one of the things I love most about Stanford. Shows up, and he shows me a plot that looks like this. I've never seen one of these plots before. This is a very grim plot. Okay? X-axis is months. Y-axis is a fraction of people in a particular cohort that are still alive. Every little bump here represents someone dying. Okay? This red line represents people with stage 1 cancer. You can see it's sort of most survivable. The line is clearly above the other two. Whereas the purple is the stage 4. You can see no one's making it past 100 months with lung cancer. Okay. Now, you may think that stage, because of the way I described it, is something that's automatic. That when you see it, everyone can tell what a stage 1 is or a stage 4 is. Turns out not the case. Pathologists only agree on stage and another thing called grade about 60% of the time. And the way they do this is they look at images, they look at the case file, and they actually argue about it. I didn't go to an actual tumor board, but I had a sort of smaller scale version of this, and I saw these two folks just argue about what part of the tumor made them think it was stage 2 or so. Now, to me, this seemed like a great opportunity for machine learning kinds of techniques. If you have one reference implementation that would every day say, like the machine learning system says it's grade 3, stage 3, you may not agree with it, but it will at least give you kind of a benchmark to figure out how are your treatments working. And a lot of your treatments are set based on what stage you're in. So we asked the simpler to get published question, not that question. Can we use images in pathology to predict the actual outcomes? Can we predict seeing what's going on here? What's going on? Where are you going to die? Okay, very good. Now, there's a really diverse prognosis in stages. Some people with stage 1 diagnosis, they die really, really quick, as shown by the drops here. And some people live for quite a long time. We wanted to understand, for those stage 1 people, is there some way to separate out the high and the low survivors? So we did about the simplest thing you can imagine. I did very, very little here. we took the images and we gave them a bunch of features. Okay, we featurized them. Zernike polynomials, old classical optics stuff, like the way you would featurize this 10 years ago. We also did a bunch of text extraction, really simple text model. We used the text to supervise the images. That allowed us to get a bunch of training data. Then we ran a logistic regressor. Okay. You could say you should run a Cox model. Turns out here you shouldn't, but you basically morally do the same thing. And you separate out in the high and the low survivor group with a pretty good p-value. We actually can find this lurking subpopulation. Super cool. Okay. Now, Kuhn did all this, put it in this paper, and the media got really excited, started talking about how AIs were going to predict all our cancers and all the rest of it, which was great. New York Times, you will not find a single quote from us in there, but they ran with that story. Okay. Now, the truth is, in some ways it did outperform expert pathologists, and that's because it had a huge information asymmetry. It could look at all the cases that it had ever seen, it could look at a huge amount of medical records, and it could do the same thing every single time. And so, there's some reason to believe that these kind of AI medical systems are actual genuine advances. That's not news. Everybody in this room probably already thinks something along those lines. What was interesting to me is while this thing was under review, something really interesting happened, almost completely unrelated to this. The New England Journal of Medicine published the following article. Okay? This is an unfair excerpt of this New England Journal of Medicine editorial on data sharing, and I'll just read it to you. A second concern held by some is that a new class of research person will emerge, persons who had nothing to do with the design and execution of the study, use another group's data for their own ends, possibly stealing from the research productivity planned by the data gatherers, or even use the data to try to disprove what the original investigators posited. There is a concern among some frontline researchers that the system will be overtaken by what some researchers have characterized as research parasites. Okay? Now, when I read this, I pretty well identified with the parasites, right? And I got right up on my high horse and started talking to friends. Look at this. I mean, isn't that science? Aren't we doing science here and overturning what people have thought? That's the bedrock of what we're up to here. I got knocked down off my high horse in a couple of slides, so hold on. But this set nerd Twitter just completely on fire. Okay, so for like a little while, some very small corner of nerd Twitter, people were super excited about this. Okay? And one of those people who were super excited about it was this guy I never met, Ido Friedberg. And Ido says, I propose a new science award, the Research Parasite Award, given to those who use someone else's data to do some really cool stuff. Okay? This guy, Casey Green, took him up on it. Okay? And luckily was well enough connected that he got Nature Genetics and a bunch of other places to actually fund this award. And even better than that, he reached out to Jeff Drazen and said, hey Jeff, can you come and present this award? Now, this is where I got knocked off my high horse. So we went out to this event where Jeff was gonna confer this award. And he then had a 45-minute talk that I don't believe was recorded, unfortunately. It was a great talk in which he outlined some of the things that the New England Journal of Medicine had had to deal with over the years. And why, even though they were using classical tools, they were fighting in a way that we kind of couldn't understand. They were fighting drug companies who weren't releasing trials. They were fighting people where they were deducing later that they were actually killing half the subjects. They had all kinds of crazy stories there. And the least of their concerns was the fact that p-values were screwed up. Okay? So the fact that we can come along and say that, hey, we have a slightly better Cox model, look at our regular, they didn't care. Okay? And I understood why they didn't care. And I also understood that their incentives were not to publish new papers, but they would run these trials for 5 or 6 or 7 years. Now, I've given some of this before, and people then send me, I've gotten so many copies of these books about how medical's research is totally screwed up. There are 1,000 books. I think I have all of them that have been FedExed to me now. I will make very clear that I don't believe that they're morally upstanding humans that are better than we are, okay? So please save the book. Okay? You can send it on a Kindle, for God's sake. Anyway, don't send me the book. Okay? In any case, but to his credit, he went out, he explained what happened, and it really made me think that we're going to have to take these tools and give them to people so they can look at failure modes that we would never anticipate. And that's not something for my lab to do. My lab can't spend 5 years per study figuring out the way GlaxoSmithKline is using the data versus somebody else. Now, of course, the shameless punchline of this is that the first award the junior class actually went to Kuhn for that paper I just mentioned, which was a really cool trip and was why I was there to begin with. But this thing really convinced us that we have to get our tools into the hands of people in a way that doesn't require someone like Kuhn to sit down and spend years understanding what the heck we're talking about. Now, in the interim, after our paper was published, 2 other papers came out that got a lot of media attention. One great paper from Sebastian Thrun, which was doing deep learning to figure out about dermatology. DeepMind also put out another paper that was also doing something related to lung cancer, which came out about a month or 2, or their announcement came out a month or 2 after our paper was published. This is the second part of what we're talking about in knowledge. Now, it turns out we also, being in Silicon Valley, we're required by law to run deep learning on anything that has images. So we also ran these models, resonance and so on. And it turned out that they did slightly better than the handcrafted model I told you about before with their Nicky polymorphs. But we didn't publish them. And the reason was we couldn't shake a feeling during what's called a red team analysis. And someone says, like, what is your model doing? I don't know. So another way to say that, or tell it by stories, is these eyes. These eyes haunt me. I'll tell you why they haunt me in a second. So every model that we build, right, we all know that they pick out unintended signals. This is why we like building them. We put weak signals into a model, we learn the weights, and oh my gosh, it has high predictive accuracy. And the model sorts out all these weak signals. And of course, in that batch of weak signals, something unintended will always sneak in. We also all know that whenever we run a deep learning model, it's not saying anything new here, but there's a lot more unintended signal that sneaks in, and they sneak in. And one of those things is graphically illustrated by these eyes. So it turns out that there are a bunch of folks, and what they were doing is looking at the iris and trying to predict the gender. And they were getting great accuracies on this problem. But then one person went and tried to replicate a bunch of their studies, and they published the following paper, which title gives away the punchline. Good title. Gender from iris or gender from mascara. Now, it turned out that what was going on under the covers and what they controlled for is it was actually recognizing the gender norms about mascara on eyes. That's great. In one sense, this is like exactly what we want from machine learning models, right? It picked up something which we never told it, it figured out the right featurization, and boom, it's able to get this prediction with like 80–85% accuracy. But it also gives us kind of a queasy feeling. If what we were reading from this model was that there's some biological link between the iris and the gender that we were pulling out with our model. So I'm not saying anything really new here. Right? A lot of people have talked about this. To do that, I'll shamelessly plug my junior colleagues. A lot of this is inspired by discussions with Percy Wang, who lives across the street from me, and Stefan Herman, both who have won great paper awards recently. You should check out their work about understanding black box models, and Stefano about really distant forms of supervision. They triple accuracy. Oh, sorry. That was like, I think about last week. Listen, I've been fine, man. I'm a little jet lag. Thanks, Nick. All right. Yeah. And he will win next year. He's that good. No. So in any event. So I'm not saying anything really new here. And there's a bunch of interesting ways to do this. We don't claim to have a lock on this problem. Lots of people are working on this. But we're going to talk at the end a little bit about how knowledge can actually help you be able to, in some ways we hope, understand and tame these models. Okay. So that all leads to this thing we're building, Snorkel. I like stupid logos. The stupid logo you'll see a lot. Okay. Now, the original motivation was that as folks were coming into our lab, we realized that they were trying to build models which to us were really routine. And I don't know about your graduate students, but if I ask them to do something they've never done before, it's like I'm asking them to commit some kind of crime against God, and they just refuse to do it. So there were lots of good problems that were coming into our lab, and we weren't able to help people because, well, we'd kind of done that before. And I understand, right? And to the point, this thing is really still, for the domain scientists, really hard to use. So, simple things we wanted to make really, really easy. Okay. Now, when I started this project, I like to give like a goal. And I don't know if you're a PI like I'm a PI, but usually I set a goal that I think is both like ridiculous and unattainable, because I always keep them busy so I can sit in a coffee shop. So the stretch goal here was that we'll have world-class quality in hours. Now what I didn't count on is that I had a bunch of new students and new postdocs, and they didn't know the rule about not listening to the PI yet. They've since learned. And they actually, as I'll show you, were really serious about this. And I'll show you some of the studies that followed it. These are a lot of the folks who did the real work on it. Stephen Bach, on the market next year, had a great ICML paper this year. You should definitely hire him. Chris Tassaw going to Cornell. Henry's going to Facebook. And these two will be on the market relatively soon. Corona's great. Alex is also good. Alex is great too. I'm just kidding. Anyway, so what are we trying to do here? 3 takeaways. We're going to try and de-skill these tasks. We're going to try and argue to you over a couple of slides at this incredibly fuzzy and squishy goal. So I don't know how to argue about it crisply, so give me a little bit of space. Then I'm going to say another thing which is probably more interesting to those of you who are doing research all the time, which is that it raises some new interesting questions. Very, very basic questions. It changes your perspective, and then all of a sudden it seems like there are 100 new questions where there were 0 before. And I'll try and get that across through a couple of examples. And then finally, there's a lot more to do. This is very, very new. I'll show you some really preliminary work on data augmentation, something we're interested in doing the theory of, work underneath. And we have a blog about related work that's been great because we've gotten a huge amount of people sending us notes saying, like, hey, you forgot this, or hey, this is interesting, or this is related. And please feel free to send us those emails. Okay? It's on that Snorkel site. Okay, so why now online overview? As I mentioned, we're in this age where people believe that model building is kind of becoming a solved problem. You can throw more GPUs at it, and then it becomes a commodity. And really, all that determines success or failure is, what data you feed. Now, I don't believe that statement in the way that I said it, but, it's a thing. People believe it. The second part of it is that to feed these models, you need huge training sets. Right? So things like ImageNet require that you spend person years literally annotating data to be able to feed and get really, really world-class performance on these models. Okay? So the point that I'm trying to get across is that in this new world, creating training sets is very, very often the bottleneck. Right? That's something that we want to attack. So this leads to this incredibly glib slide here, that training data, not data, is the new oil. What I mean is that your models and your progress is gated on having access to enough training data. This is really a fundamental problem. It's not about text, it's not about images, it's just something that happens with machine learning. Now, at first blush, telling you that you need more training data to train a better model is a lot like telling you you need money to be rich. It's true, but it's not super helpful. What we're going to do instead is make a simple observation. Our simple observation is that every realistic training set that I'm aware of is created by a process. Someone put it together, labeled some pieces, wrote scripts for other pieces, and assembled it. And what we're going to do is we're going to model that process. Now, if your process is perfect and it generates absolutely gold data every single time, then what we're going to tell you is not going to help you. If your process has a couple of bugs, a little bit sloppy, maybe we'll be able to correct some of it. The really exciting stuff comes when you start to generate training data in entirely new ways because you can tolerate the fact that only 60% of the points that you generated with a given heuristic are actually valuable. And that's this idea that we call data programming. Okay? So that's what Snorkel is all about, modeling that training set creation process and trying to get you to sort of supervise in as sloppy a way as possible. All right, so let me give you an example to make it very concrete. We've been talking pretty high level. Let me drop to a really, really painfully low level. So we want to build data extraction systems. Right now they take months or years and a PhD student. Instead, we'd like to build them in hours. Okay? What's holding us back? All right, so here's the task. I don't expect you to read this text. This is something we'd like to do. You give me some text. I'd like to be able to produce a table that looks like this one, that says this particular chemical causes this disease. Okay? Read the text, show me what are asserted as causes. It's also known as relation extraction. How does this work today? So the way it works is the first step of what you do is something called candidate extraction, if you haven't ever built one of these models. This is a step where you're very permissive. You have lists of, say, all of the chemicals that you want. You have regular expressions that may or may not match a disease. More precisely, you're optimizing for recall, not precision. Okay? You may have one useful candidate out of 10 that is actually matching your model. That's okay. Throw it in there. Okay? The next step is that you then go and annotate a training set. Because the candidates are unbalanced, which is usually a pretty unbalanced training set, you annotate a bunch of those different models. Then you perform this step, these classically feature engineering. And to be clear, for the highest quality models, you still have to do this step. And then you do learning and inference. Okay? So this is sort of a pipeline. Nothing surprising. Now what is surprising is that a lot of these things are actually going away. So candidate extraction, we had some little paper where we just tried different candidate extraction strategies. And it turns out you can be pretty bad at candidate extraction so long as you have enough training data. If you have enough training data, you can just throw out n-grams or use Elasticsearch or do something really simple and generate these candidates really permissively. Operationally, when a bio-person shows up in my lab, candidate extraction is not where they spend their time. Learning and inference. Although it pains me, and we have a paper out from the lab this year about petascale deep learning and all this other stuff on, petaflops of whatever, it turns out that for most problems, learning and inference is also not the bottleneck. It runs comfortably on your laptop or an AWS server that you can get access to for most of the problems that people care about. The feature extraction is a little bit more interesting. Okay? It used to be that this was the bottleneck. We spent a bunch of time trying to think about that. Now, I'll throw this slide up here. You can agree with it or not, from one of Chris Manning's recent keynotes. And this summarizes kind of what the belief is in some ways. That there's this bidirectional LSTM, and it's to a first approximation, getting you state-of-the-art at whatever task you throw at it. Now, that's not perfectly true. That's okay. But really what's going on here is that for a lot of tasks, you can actually do pretty well with these things. And it's arguable that a model that does 5 or 10 points better in F1 is really so critical for biologists who are doing their analysis. So in this way, if you kind of look and extrapolate wildly and without control, you can kind of think of feature engineering as dying as well. We'll cross that one off just for the sake of argument. But all this stuff that I just told you, is all predicated on the idea that you have massive training sets. Because you need massive training sets to separate signal from noise and candidate extraction. You need to learn not only the weights of the model, but also its representation. And all of these things require a huge, huge amount of training data. So this is the idea. How are we going to generate it? We're going to model the noise in the training set construction process. And this is going to allow us to use many different sources. So many kinds of sources, crowdsourcing, distance supervision, all of them in different ways at once. And they're going to be even lower quality than you would traditionally use them. And this will let you build them very, very quickly. And we're going to do that and still train high-quality models. Okay? That's going to be our goal. So this is how it works in Snorkel. Okay? Let me just give you a concrete instantiation of how this thing runs in one example. So what happens is the user loads in a bunch of unlabeled data, text. They're going to write these things called labeling functions. I'll illustrate one by example, but it's just a function that's going to assign 1, -1, or I don't know for binary classification. Okay? It doesn't have to say, it doesn't have to vote, but it can just kind of vote. You can do more complicated stuff. Then you choose a discriminative model, right? LSTMs. Underneath the covers, what Snorkel's going to do, it's going to take your big unlabeled training set, and it's going to heuristically label a whole bunch of them by applying labeling functions to the data. It's going to keep track of where these labeling functions conflict and who generated what point. So instead of a big, undifferentiated training set, you're going to know where every point came from. You keep its provenance. You're then going to learn a model of the noise. So you're going to know that some of these labeling functions are very accurate, and some of them are not very accurate. And you're even going to learn correlations, as we'll talk about. And then you're going to use all this noise modeling to figure out how to train a noise-aware discriminative model. So let's go through those steps. Okay. Importantly, I should say there's no hand-labeled data absolutely anywhere inside this process. We're going to do everything without labels, and that's what makes a bunch of questions that are sort of theoretically interesting pop up. So the main user input now, which is important, is to have one slot to put information in. I can't tell you how important that is. It seems to just be monstrously important that when teaching people to use the system, they just write labeling functions. Okay, so here's an example of labeling functions that will be familiar to NLP people. Distance supervision. You have a big knowledge base of chemicals and diseases, and you have sentences. And what you're going to do is for every sentence where the two pairs, the chemical and the disease, that you've heuristically extracted are in your database, you're going to state that that's true. Now this is likely to be true, but not always, right? Because it could say chemical A was found on the floor in your disease B. It doesn't indicate causation. But that's okay, your model will hopefully sort it out. Now what we're going to learn here is that we're going to learn the accuracy of this rule. Right now it's an impossible problem. If we just have one rule, how can we learn its accuracy? And moreover, why would it really matter? You just kind of regularize away. But if you have many different rules with differing quality, you don't need their labels to be able to recover their accuracies. And that's going to allow us to program in kind of a new way by sloppily writing lots and lots of labeling functions. So what can you write? You can write all those distance supervision, regular expressions, and text. You can put crowdsourcing. We have demos about how to put crowdsourcing those things together. You can think about it like boosting and throw a ton of weak classifiers or other models. You can have domain knowledge that you inject in some crazy way. People have done all of these things since we released it. Now what we need to make this program work is a formal way of capturing what these models are doing. And our choices are relatively simple and standard ones. We're just going to use standard graphical models, generative graphical models, to understand what's going on here, and view these things as a noise-generating process. So I should also point out that users can define dependencies. And in fact, Bach has a great paper about learning those dependencies, which I'll share with you. Again, we can learn those dependency structure, without any labels. And that changes the problem. And we'll talk about how it changes the problem. And we can even learn some conditions or functions, and Paroma did that. Very, very cool. All about labels. Now, the first thing I want to show you is that actually this works. That is, we had bio people come into the lab. We kind of sat next to them and guided them. And we showed them that for a particular task that they cared about, we could actually meet and sometimes exceed supervised benchmarks just using this approach. So there's no funny business here. Actually, with just a couple of labeling functions, you can actually meet or even exceed the F1 scores that come back from these benchmarks. You can do it pretty quickly. Now, when I told you that my postdocs and PIs didn't listen to me, this character, Jason, actually went and invited some folks with an NIH center that we're associated with. and said, hey, do you have something you'd like to build in this kind of text extraction domain? Why don't you come visit us for 7 hours and we'll help you build a model, okay? So this is getting close to that, we'll try and get you world-class quality in a couple of hours. This is a pretty tough test because these are people we don't know or control, and they come from all over the place. And so he actually ran this workshop a couple of weeks ago, and kudos to him for preparing it and getting it out there. Now I won't dig into these details too much of what's going on here, but the point is that using the best Snorkel model versus the crowdsourced model, it's a pretty substantial bump in doing it this way. And everyone, except for one person, was able to complete the tutorial. And why do I call that one person out? Because every graduate student here knows who that is. It was a PI. So the only person who didn't get through it was a professor. Anyway, so the thing is, afterwards, there was some Twitter talk about it. And one of the things is this woman, talks about how, for a newbie, she didn't know anything about text mining. She wrote pretty good, labeling functions. Her score actually went up afterwards because we did some automatic tuning underneath the covers. But my point is, these were sort of Python novices. And to support that point is this chart, which shows that the F1 score someone obtained and sliced the data in 2 ways, really preliminarily. And you see that sort of what matters more in terms of final quality is programming experience, not text mining. This is what we were looking for, because it means that if you think about how it could be effective in 7 hours, it should be someone who knows programming, but it shouldn't really be correlated with their text mining ability. It shouldn't have, if we've done our job well enough, it should look sort of like this. So that was pretty exciting. Okay, so last little bits of tidbits that I want to tell you about Snorkel before talking about more technical challenges. The first thing is that everything is supervision. This makes it pretty easy, and it changes the experience fundamentally. Rather than having to write a bunch of features and then supervise your data and then run the model, you write a couple of labeling functions and you get an answer almost instantly. It's just like dynamic debugging. It's the same thing of going from compiled languages to a REPL. It's that same kind of change in experience, like using Python rather than C. It's super easy. The second thing, which I'm not sure I believe, but is this idea that it's easier for people to write these labeling functions more than features. And the reasoning here is that, well, features have this kind of statistical character to them. You have to know, how to separate your data well and a bunch of other things that are mysterious to people. I think it's just that they can iterate faster, and I can't substantiate that statement. The second thing is that people really like programming in these really high precision ways. They like getting the high recall of the underlying deep models. So always the generative model has really high precision and relatively low recall. But the LSTM basically generalizes for them and gets them much higher recall. That's all that's really going on here under the covers. And the last bit is the one that to me is most conceptually exciting, which is now supervision as code. And the reason that's significant is that you can take that code and use it for new tasks. So people actually did take the labels that they learned on the demo and started to use them for their own research, almost verbatim. And also, another exciting thing is that as you get more unlabeled data, your quality just goes up, right? And that's spectacular because it's easy to acquire sort of unlabeled PDFs and just let the system run for a little bit longer. And that's a really nice feature. So what's the technical challenge? I told you a lot about the sort of software engineering side of things. Well, what's really going on here? Well, the challenge and one of the perspective changes is that we're now dealing with training sets that have really uneven quality. Traditionally in distant supervision, you assumed everything was kind of uniform quality and you just used regularization to fix the noise. But here, we're going to have vastly different kinds of quality inside the system. So here's a story to illustrate why this is so challenging, and it's real. It actually happened to one of our users. So one of our users actually wrote, in this old DeepDive system, wrote a bunch of labeling functions, basically to do distant supervision, and had 10,000 points at 90% accuracy. Okay, so labeled a bunch of data. Then, unbeknownst to them actually, they wrote a very low precision rule, 60% accuracy, but had huge coverage. So they labeled 1 million points at 60% accuracy. If you don't model the lineage, you don't know that there are high precision and low precision points. Kind of obviously, it just becomes a big mix and sea of undifferentiated labeling set. And in fact, you get down to 60.3% accuracy. From the point of view of the user, it's extremely frustrating because now they just added a rule and their quality gets worse. And worse, no matter how much of the good stuff they do up here, they really can't move the needle to get the quality to go up. Now the solution is relatively simple. Just know where the training points come from, and you can downweight these points substantially if you knew that they were low quality. And so that's what we're going to try and do. Okay? So how does that work? What we're going to do in the first step is we're going to learn a generative model for the noise. We're going to learn its parameters without labels. And then we're going to feed those things in the second step to a noise-aware model. Think about it as a big LSTM or a logistic regressor, and you'll be able to feed this sort of noise on the training points through. So how does it work? which hopefully will look really simple. I'm going to pick a very simple case that will hopefully look the most like crowdsourcing or matrix factorization to you, depending on your background. So here's the idea. We have a bunch of these labeling functions. We have a bunch of objects. And the labeling functions are going to vote. Okay? What we observe is all the votes and all importantly where they conflict and where they agree. And what that's going to allow us to do is if we imagine we knew the accuracy of all the training set, it'd be really easy to back out the accuracy parameter. But if we imagine everybody else is okay and we're not, we can still kind of make a guess at our accuracy parameter. This is just another way of saying it's just a sort of constrained matrix factorization problem. Or however you like. Think about it as a crowdsourcing problem. The majority eventually gets consistent. However you want to think about it. Now, it turns out the scaling is different from what's in the crowdsourcing literature in some technical ways. And that requires us to prove a couple of new theorems. But morally, it's the same. We find the accuracies, or in general, the parameters of this graphical model, and then we use forward inference to figure out how accurate, how much we trust every one of the points. How do we feed it to the model downstream? Well, if we have an empirical loss that looks like this, there are many ways to do it. One is to just make the loss stochastic and sample from the underlying distribution that you've just estimated with your generative model. And this is a simple tweak. You can do this to almost any model. There's no magic here. All right. So the theorem that we show underneath this is that under some technical assumptions, basically that the labeling functions conflict enough so that you get information. The labeling functions never overlap. There's nothing you can learn. So they have to overlap and conflict sometimes. But you can show, and if their accuracy, the sum of the accuracies is bounded away from what would effectively be 0, or a half. They're not noise. Then you can show that you can actually recover the parameters of the underlying model. And moreover, you can show that the value of these points that you're generating is within a constant factor of actual labeled data. You get the same kind of sort of generalization bounds as you would get in a supervised setting. And even when you have dependencies, and I showed the simple case that looks like crowdsourcing, but when you start to have dependencies, things get a little nastier. You can even show analogs of exactly this theorem, although the conditions that you need get correspondingly a little bit nastier. Now, the real question is, does it work? And what we did, the first thing we did is take this old benchmark, which was TAC-ABP, that DeepDive had won, which was this old benchmark that was out there, and we applied it. And we actually saw that we got a 2-point bump in F1, about 8%. It's a really hard benchmark. We took the best LSTM that was in the competition, that was substantially lower than any of the hand-tuned systems, and we jumped it up to second place, just using this technique that I described. Even a manually curated distance supervision approach, which we had used previously and tried to clean up the data, also only gave it this, sort of a smaller bump. And so you see these decent quality gains in a number of settings. It's not the difference between working and not working. It's not magic. But it has quality bumps that are actually comparable in some applications to the difference between using an LSTM and using bag of worms. Okay? So it's a trick in your toolkit. It also improves both human features and deep learning features. You may be concerned that there's some kind of weird intersection between your labeling functions and human constructed features. And indeed, it's easy to come up with cases that you could imagine this happens. Turns out it really doesn't, though. And actually, both human and deep learning features improve. These are cross-validated numbers, no weirdness going on across them. These are on a hand-validated set that was not generated by the same people who generated the labeling functions. All right. What's weird is we put this online. There's been a usable version for about a little less than a year. There are tens of users that are using it daily. It's in production at a couple of different places on a daily basis, which is super exciting. And we're excited that someone can actually use it. As I mentioned, this idea probably is similar to something you've already heard, except that every person in this room thinks it's similar to something else. Okay? So send us what that something else is, especially if you don't see it on this blog. But it was certainly inspired by a bunch of these different things. But the perspective of using supervision as your programming mechanism, I think, is actually quite distinct and different. Many more things in this than we've read about these things. Great, great work. So please, the web page is there. Send us a bunch of people. So now one of the things I promised you was that we would have a new perspective on some classical problems. So one of the most classical problems that's around to me is estimating parameters of graphical models. 10 years ago, that's what this conference would have been about. It's classical. Right? This work was done by Stephen Bach, Alex Ratner, and Brian Heath. They had this paper last week at ICML. Really interesting paper. Okay, so what is learning the structure of a generative model? We're just going to take binary factors. We extend the hierarchy stuff in the paper. The idea here is you have these labeling functions, and you have a true label. The problem is you don't get to see the true label. Okay? So traditionally, you get to see the true label, and what you want to do is, in both cases, you want to understand how are these guys correlated. And there are all different ways that they could potentially be correlated. You want to learn which links are present in the underlying factor graph. Now, the problem, as I said, is that everyone depends on that hidden label. And this causes two problems. The first is really an analysis problem. The previous best results that we were aware of, this kind of L1 regularized thing from Robert Kumar and Wainwright, required to type the Lagrangian duality gap. But this problem's not convex any longer once you have this latent hidden variable. And operationally, that argument just doesn't go through. And actually, if it did go through, it would be wrong, so can't go through. Okay? It doesn't scale, it doesn't give you the right scaling in terms of the parameters. So now we have this non-convex problem, and this is actually, so although it may not seem like it from the first part of the talk, I spend most of my time actually proving theorems. This actually is like a sort of non-convex, but it's one of the nice ones. So it's one of the nice ones in that it has a whole bunch of symmetry underneath it covers. And that symmetry allows us to basically figure out, once we know the symmetries of the underlying problem, figure out like so where it's sort of locally, or I would say kind of morally convex. Not really convex. So what we can show is that for pairwise dependencies, we get a sublinear rate. This is better than I would have expected at first. We don't depend on the number of edges. We just depend on the number of nodes. Okay? That's pretty nice. Now, what the statement says is we need n samples, where m is greater than n, and then there's some log factors here, which don't really matter too much. What you would expect, and kind of with high probability. Now the probe here is that we don't need any labels to prove this. That's where the things got sticky because of that lack of ability to get our hands on firmly what the label is. And that's why we had to check all the different pairs underneath the covers. The con is that we have much worse dependency on the sparsity. The traditional dependence on the sparsity should be something that poly d. So if d is your sparsity, it should be polynomial. The Robert Kumar and Wainwright paper was d cubed. The true dependence is probably d3 halves, something like that. Still, it had d as a sparsity. So if you have a really sparse model, we're going to have to inspect all the edges, all the nodes, whereas they'll be able to zoom in on them much, much more quickly. Okay. In any case, so that's what you give up when you go to this unlabeled path. And what I wanted to show you is that actually there's kind of interesting theory here in a really simple model that's actually pretty practically well motivated. Another thing that goes on underneath the covers is that to actually do the estimation sort of properly and solve the underlying optimization problem, you would run some kind of MLE typically. And what this is showing is just a simple stupid heuristic, which we can prove works, which is a pseudo-likelihood method that's 100 times faster. And why this is so cool is because it means that you can now run nearly interactively, solving with the pseudo-likelihood in place of the original MLE, and still provably recover under appropriate conditions. What's, to me, most exciting is that it actually works. Okay? So when we put this thing inside Snorkel, people were not knowing that we could figure out correlations, so they were writing them, trying to make them as orthogonal or as independent as possible, depending on your terminology. And just looking back at applications that people had really written by looking at our users, we actually saw pretty healthy F1 bumps for modeling the correlations underneath the cover. Again, a couple of F1 points, and then the difference in different automatic featurization approaches. Not working to not working, working to not working, but still kind of interesting. Okay. Now, one thing that I'll skip through very quickly is that, as I mentioned, this changed absolutely everything that was going on inside our lab. And there's this weird buzzword that I both hate and love about making things ML first or AI first. Okay? Now, companies use this to recruit people like you. But what I think it actually means is that there are a bunch of tasks that right now we all kind of know that machine learning would do a really good job at. But we don't use them, or engineers don't use them, because it's too hard. Well, it takes too much effort. And so we started figuring out, okay, well, if we have this new hammer, let's go around and see which of the low-hanging fruit we can scoop up and try and solve a bunch of what used to be sort of classically hard problems where people didn't run machine learning and see if we can do well. One of the ones that my postdoc Theo did, Theo's now going to be at Wisconsin, she's going to be at Georgia Tech. That's he's an old guy from Water. Anyway, you don't have to plug it. Anyway, but they ran this thing on data cleaning, which is like a classical database problem, against industrial competitors. You can look up their affiliations if you don't believe me. And really good industrial competitors, and they got amazing numbers, like 90% precision, 2x higher F1 score than the previous state-of-the-art on this. They did everything in a weekly supervised way. And this is appearing in Munich in about 2 weeks. But again, the idea here is this stupid idea seems to dramatically change kind of what problems we attack. Another one that Sen did, which is amazing, is actually reading part sheets. So part sheets are incredibly difficult to read. They have no semantics in them. The semantics is visual, and it's textual, and it's kind of weird. And so he built this system, this deeply supervised system. It's online. It's called Fondue. I don't know why it's called that. It's something to do with fondue. He likes fondue. I don't know. Anyway, but he built this thing. And these people started using it. They actually started using it. In fact, one guy who lives in the lab downstairs or across the street, I don't remember which, Volodymyr, actually used this and is now submitting a paper about building one of the largest what's called GWAS databases. So GWAS are these genome-wide association studies, and he just picked up the tool and started extracting them from tables and papers and got a larger database, which is super cool, and got a bunch of new ones that weren't in the database. All I've talked about is text so far, but I want to plug what is honestly to be some of the most exciting work that Paroma's doing with bone tumor stuff, and she did some stuff with Feifei's group on complex image queries. You can do the same things over images, but you have to have different vocabulary. Instead of having like a primitive of words, you have to have like primitives that are like object detectors. And you can do higher level stuff, and she's shown that you can actually even beat some of their supervised baselines that I know they spent years constructing, basically with a couple of rules. Super exciting stuff. Her blog post will be up soon, and she'll post her paper hopefully relatively soon. All right. The last thing that I wanted to try and get across with my remaining time is just that weak supervision isn't just doing a bunch of noisy labels. There's something I'm really excited about and I know next to nothing about, so that's not going to stop me from talking about it. So the idea here is to look at data augmentation. So I've been reading some of the DeepDive papers, and what I noticed in a lot of their papers is that you see this awesome thing, which is they get these great results. And then there's always, except for some of the best papers, something which said we augmented our data. And they just like say something like that. I'm like, well, what do you do? Now, if you look in some of these like recent papers, when we actually went and catalog, what they mean when they say we augmented our data, an amazing amount of research intensity goes into there. Every layer is supervised and forced in a different way. They rotate. I mean, it's amazing what goes in there. And sometimes it's just a sentence. Okay. So we started this project called Tanda to try and understand like what was going on there. We eventually want to prove theorems. We have like a LaTeX file, but we don't have anything we're ready to share. But we decided to conduct a bunch of empirical experiments. And they all started with those eyes again, where we were like, what's going on with the eyes? How could we help improve the situation with these sort of eyes and this unintended signal? And so what our naive thought was, what if we knew some invariance about the domain? So when we were looking at cancer images, we knew that they should be rotationally invariant. We're looking at a slide full of cells. Spinning them around shouldn't change the class. Right? So you don't know it ahead of time. So maybe by putting that in, that more mechanistic knowledge, we would get out more robust models. Now, the first thing we tried to do was bake it into the models themselves. We couldn't get that to work. Right? We built models that were actually rotationally invariant deep learning models. They didn't do that well. What seemed to work better, and there are a couple of papers actually already going in this direction, is to just take the training data and augment it, spin your training points in some different way. So we saw a bunch of people in images. They would do rotations and scalings and brightness and color shifts. In text, there are a bunch of really cool papers about taking programs and swapping out synonyms and doing all kinds of things, taking trees and sticking them together. In the medical domain, we saw people doing this basically, kind of willy-nilly. It was awesome. They would take tumors and move them around, or lesions and move them around on people, and resample and do kind of blending in Photoshop and generate kind of realistically looking images of that. And so he said, how do you, if these transformations aren't all equally good, you can go wrong with that. And the order in which you apply them can be wacky. Maybe there's some theory there. We can get, again, kind of like a simple bump that says, like, if we model the order, we model equality, maybe we can do a good job and then change the job of the person from having to write down this crazy sequence of, modify it this way, spin it that way, spin yourself around twice, and then shrink it, to go like, hey, here's some declarative way of looking at it. Maybe we can model that process. So we did that. They did this thing where they tried to learn sequences of transformations. They did it in an adversarial way. Not sure that they had to, but they liked it. So it was cool. And they learned sequences of these transformations, and actually which of them are good or bad. I'll just show you some numbers. There's a whole blog post about this. The point is they learned to avoid catastrophic kinds of transformations pretty well, almost automatically. And they actually did get pretty good bumps for various things like CFAR and some others. So pretty exciting stuff.
In terms of efficiency, isn't that a little bit overwhelming in the sense? Shouldn't you work on the algorithm side so that your algorithm is, let's say, translation invariant rather than generating petabytes of data?
Yeah, so that's a great question. So the next question is like, shouldn't you do the first thing that I proposed, not the second thing? And I also agree with you. That's how it should work. So the first thing we did actually was change the model to use parameterizations that were rotationally invariant, right? And they have two problems. So those are something called Zernike polynomials. So you take them, you write them down, you know they're rotationally invariant. The question is, as you start to compose more and more of the invariants, it gets more and more difficult to put that information into the model. That's not to say it's a bad choice, it's just to say that that calculus is difficult to work out. So that's one point. So if you could do that, it seems preferable because you're sort of directly going after the model.
Is there anything we can learn from the other, things we've done in relational machine learning where, we don't have to normalize the database and people can do machine learning on the relational domain in complex ways?
Excellent point. So without tipping my hand too much because it's my students' results, it turns out that actually there's a way to think about this process as defining some underlying space. There's some association here between augmentation and kernels. And it turns out that then you don't actually have to write down all of these different functions. You can actually do some interesting biasing and some interesting sampling. But here we don't know how to do that. And we wanted to see if within this, we basically wanted to take transformations people were already doing and see if there's a sort of way to redo them and sort of automate that. But you're right, there's a massive cost. We're going to run huge numbers of transformation functions and learn all kinds of crazy stuff and work like, look like a worse parody of sort of GPU logs. Yeah, you're exactly right. You got it.
Compute is cheap, people are expensive.
What?
Compute is cheap, people are expensive.
Well, in some regimes, up to a point. Yeah. So, in any case, the point that I wanted to make here is that we can run this over a bunch of different models, and it actually gets some performance improvement. In some of these cases, these are folks who have actually hand-engineered their models, so being able to even get little improvements there is pretty cool. We can use arbitrary end models, and it's interesting to do. But I think I think what Nick's getting at, which I definitely agree with, is we're not at the end of the story here, and there's a big call to try and figure out, in my mind, what's going on with data augmentation and the rest. And that's something my lab I'm really excited about. I admit I was scribbling furiously on the plane thinking about it. So maybe if you talk to me next week, I would be that interested in it. I don't know. But yeah, so this is what's going on here. So that's really all I wanted to say. So there's 3 things that I wanted you to take away. The first is this whole thing about dark data. And that it can have a positive impact. And what we learned from there, at least from our lab, our sort of takeaway, is that getting these tools in the hands of other folks is extremely empowering. And it's going to, we think, hopefully make ML and AI take this big next step that we really are excited about. We want to make these things radically easier to use, and we decided to focus on supervision. Now, maybe it's the right thing to do, maybe it's not. I have actually no idea. But I think it's interesting because it's an area that has almost no structure. If you look at these models, we've done a lot in terms of model building, but there's this whole wild and woolly thing. And if you'd said 5 years ago, I gave a talk about how we should think really about how to automatically do feature engineering in NIST. And I remember someone stood up and said, that that's outside what we study here. I'm like, well, okay, that makes it interesting, right? I mean, if it's new and crazy and weird, we should spend some resources on it because maybe it goes somewhere. You don't have to agree. The last bit is, please don't hesitate to send us pointers of things that you think are related. We've had some really interesting discussions where people say, that's exactly what I think I'm doing. Let's talk about it. And then we realize after talking to each other for an hour by Skype, we're doing completely different things. But we learned there's some common core that's really exciting. As a result of that, we're trying to keep a blog up to date that was written by some of my students, some of Stephanie's students, to try and figure out what's going on here. Thanks so much. I appreciate your time and attention.